Okay, welcome back. This next video is on Microchip Incorporated. Microchip, as we know, is the leading provider of microcontroller and analog semiconductors, and it provides the development tools that we're going to be using in our class. Particularly, three things we're going to look at. The MPLAB X IDE, which can run on all the platforms that are common these days between Windows, Linux, and Mac. So it runs on actually a NetBeans platform. The compilers that we will be using are just the XC16, and then the programmer over here you can see on the right is the PicKit3, which flashes our code to our chip. Microchip is headquartered in a place called Chandler, Arizona, which is just outside of Phoenix. Okay, the PIC microcontrollers that Microchip uses use the same language for all the PIC products. So we can program in C, and we can program also in assembler or assembly language, which is very low level language. PICs are very cost effective when you compare them to say Arduinos or PICAXes or PIC Basics. So they're very affordable chips. The software is free, and they're just a load of resources. So if you look at this map here of their entire scale of product or their product line, we'll be using the PIC24F, which is in the middle, and you can see how that's part of the 16-bit microcontroller family. I used to use the PIC16 right here, which is an 8-bit microcontroller, but the 16-bit offers a lot more features that we need for our robot, so that's why I moved up on the advice of my friend Dennis Sessick at Microchip, and it's been great advice. So thanks, Dennis. So let's look at microchip.com for some of the resources we're going to need. If we download the latest versions of MPLAB X IDE and the XC16 compiler, which are free, it's very easy to do. And then we're also going to look at two pieces of documentation. We're just going to look at this one for now, which is the data sheet for the family of microcontrollers that we're going to be using. So if I go to microchip.com, as I'm here in this website, I am going to scroll at the top here. You'll see these tabs to design support, and I'm going to go down to data sheets. So as that loads, okay, I can then find the data sheets that I want by typing in, okay, the PIC 24 FV 32 KA 304. Okay, and if I hit enter there, or if I go up here and say contains, it will pop up all of these different microcontrollers. Now the important thing to remember with this data sheet is it contains all the information for all of these microcontrollers. This is the one we're actually going to be using, the PIC24F, the FV, which isn't even here, 32KA302. So it's not listed here, but I will show you where it is in the data sheet. But that data sheet contains information on multiple microcontrollers that are part of that same family. So if you type in the number of our PIC, which is the FV32K302, there isn't a separate data sheet for that microcontroller. So what should happen if you download that? You should get this data sheet right here. And it contains a lot of useful information, not all of which you're going to be using. There's 320 pages in this data sheet. I would never expect you to know all that, but there are some useful reference materials that you can access here to really better your understanding of what you're using with this PIC. So if we scroll down here, again, I'm going to go to this particular family chart here, and you'll see that again it lists all those devices as part of the family, and we're going to be using, if I highlight this across here, we're going to use this FV, okay, this FV32KA302. And it just summarizes some of the physical features, such as 28 pins, has 32K of program memory, 2K of data RAM, 5 timers. It also has 3 output PWMs for our motors to control the speed. And we'll be using these this 13 channels of analog to digital conversion. We won't be using all 13, but That's a really important part of what we're going to be doing this semester. And comparators and other things there that we don't really need to know about. So if we scroll down again to look at some of the pin diagrams, you'll see this first one, which is the 20 pin. We're not using that one, but you can see it's a shorter pick. Doesn't contain as many resources. And the next one is the one that we're going to use. I'll come back to this in a sec, but if I just scroll past it, you'll see that these other ones are surface mount chips. You can see how the pins are on all four sides of the chip here because it's machine soldered onto a printed circuit board. Whereas the one we're using, okay, which is this one here, is a DIP, which is dual inline packaging, which fits on a breadboard, which is perfect for our purposes. So let's look at these pins. You notice right away that there's a lot of information here. So let's look at how can we separate that. Well, this is the FV side. This is the F side over here on the right side. So we want to focus on this left side only. And just to highlight again, you'll see that there are a lot of features or pins that are shared. They have shared functionality. So this first pin, pin 1, is the master clear, and that will reset your pick. But it's also shared with VPP, which is the programmer pin, which is where the executable or hex file gets downloaded into the pick. And then it's also shared with RA5. So as a result of that, we actually don't even use RA5. Another example could be if we're looking at, say, RB1. Well, RB1 is a digital input or output, and AN3 is a digital is an analog input. So we cannot have those two operating at the same time, but it's really important that we set those pins to either be using analog or digital. We can't use them both. And in fact, this pick and all microchip picks default to analog first. So there'll be things later on that we'll learn about. So you can take a look at all the other features here, how they're shared, and just do some exploring there. Okay, so that concludes this video on microchip and the PIC family of microcontrollers that we're going to be looking at.